Recording.
Oh, I'm supposed to say something. Oh, I'm sorry. Uh, well, welcome to the monthly heliophysics discoveries and topics session. We've been doing this for gosh, about getting close to a year and a half now, every month, and it's been, a pretty interesting experience for me as a presenter. And I think we've had, typically, 40 to 60 people registering, and a pretty good crowd actually showing up in person. So it's been a very worthwhile experience, I think, for everyone here. Um, this topic that we're going to cover is one of a variety of topics. In heliophysics, uh, we like to think about three big questions that this particular subject in astronomy addresses. What causes the sun to vary, and how do the Earth and the heliosphere respond? And what are the impacts on humanity? Um, these are part of what is called the big questions in heliophysics. Each of the four different theme research areas at NASA have their own big questions. Um, we've created this framework for heliophysics education as a way of going from these big questions to specific education standards. And we do this through the framework, as we call it. Um, there are a variety of subsidiary questions under each of these three big questions. And each of those subsidiary questions address a specific set of next generation science standards, which are given in the parentheses. This evening, I'm going to be talking about a subject that addresses how the sun defines the space around it, which is different from interstellar space, and something about the energy from the sun flows outwards through the sun and into the heliosphere. And as it does, it creates a variety of phenomena that we study in heliophysics. One of the things that, of course, the sun does is to heat up our atmosphere. And our atmosphere, at least the one on Earth, is remarkably thin. In fact, if you bicycled from Baltimore to Washington, or if you drove your car from San Francisco to Sacramento, you'd basically be traveling a distance that's equivalent to most of the atmosphere of the Earth is sort of that thin compared to the actual size of the Earth. So it's a very thin layer, and it's very fragile, as we all know from climate change and global warming. But one of the things that happens to atmospheres living near stars is that the stars themselves can produce a variety of phenomena, specifically something called a solar wind, which is a stream of particles that comes off of the hot surface of the sun and flows out into interplanetary space. And as it does this, it will encounter the atmospheres of all of the planets in the solar system. And sometimes that encounter is not particularly benign, and it can cause the atmosphere to be ejected with a really strong wind. Or it could just be kind of a troublesome thing that doesn't really do a whole lot over a short period of time. Our atmosphere, as you know, is a variety of layers, and each layer, as you move out from the surface of the Earth, is progressively less dense than the one below it, until finally you get out to 300 to 400 kilometers, where it's almost a very good vacuum. There are so few particles per cubic centimeter. And this is the domain of low-flying satellites and the International Space Station and things like that. You can actually measure this outer layer of the Earth's atmosphere. We call it the geocorona, which is something that's actually visible from the surface of the moon. And you can actually take a photograph of it if you have the right technology. And you can see that it's a very extended atmosphere. It reaches almost halfway to the orbit of the moon. and it gets progressively less dense the farther out you go from the Earth, as this uh, curve shows, which basically is curving towards lower densities as the altitude increases along the curve. And so as a result, you have at the outskirts of the atmosphere, you have a very thin atmosphere, but you still have this solar wind coming into contact with this very dilute and thin atmosphere. The result is that the outer layers of the Earth's atmosphere are constantly being ejected into interplanetary space by collision with the solar wind particles, which are mostly hydrogen atoms or protons. There are other mechanisms that can cause a planet to lose its atmosphere. These are the four big ones: photodissociation, X-ray heating, something called the Jeans mechanism, which I'm not going to go into, and then finally, one I'll talk about tonight, which is sort of the easiest one to think about, is the solar wind. Uh, Currently, Earth's atmosphere is about 5,000 trillion tons of material. It's losing about 95,000 tons per year of its hydrogen and progressively less material as you get to the heavier elements. But 95,000 tons per year of the geocorona hydrogen is what we're going to try to understand this evening using a toy model. Scientists like to build toy models on the back of envelopes to get them a sense of scale, to convince them that they understand what the most important processes are when they're trying to model a particular phenomenon. And then after they have a toy model that they like, they then take it to the next step. Of course, they compare the prediction from their toy model against what the actual data is. And then it's a process of iterating on the toy model, adding in more complexity, more definitive equations that define specific processes and interactions, until finally you get to a level of modeling that's actually extremely sophisticated. Often it needs to be run on a supercomputer, and often it nails the observed data to within a few percent accuracy. So it's an interesting iterative process, and what I'm going to do is to show you what sort of the beginning of that process looks like. Here's the solar wind, kind of an animation of it hitting a planetary atmosphere. Well, it looks a lot worse than it actually is. You don't see the solar wind, and you actually don't see the particles in the atmosphere flowing out the way they do. But this is an animation that sort of explains and shows, what the basic mechanism is. Here's sort of another artist's rendition. You've got the streaming of particles from the sun's corona in the solar wind, and it comes out, makes contact with the atmosphere of the planet on the sun side of the planet. And then it flows around and strips the atmosphere from sort of the tangent points and the backside, producing a kind of a comet-like plume of ejected atmosphere on the backside of the planet. Here's another animation of what this looks like. Once again, this is not a computer model. This is just an animation to give you a general sense for what the dynamics look like. And what we're going to do is we're going to look at a few basic ideas. Basically, the solar wind is mostly of protons. That's the dominant element, the dominant composition. The atmosphere of the Earth is mostly hydrogen and is of pretty much uniform density, we're going to assume. And we're also going to assume that every proton that collides in the solar wind with a hydrogen atom in the atmosphere ejects exactly one hydrogen atom. So that's the toy model. It's making some assumptions. There are three here. And they're basically just simplifying assumptions we're going to use just to get the calculation started. Well, here's geometrically what this collision looks like. Solar wind enters from the right. It approaches the planet. It interacts with the blue hydrogen atoms in the atmosphere. Uh, in the zone where it's sort of approaching the disk of the planet, essentially the hydrogen atoms are sort of driven deeper into the atmosphere, so they don't escape really. But in that tangent space, you have, which is above the disk of the planet, you do have the opportunity that a collision with a hydrogen atom is going to cause the hydrogen atom to escape or not to escape. Our assumption is that every one of these collisions causes an escape. So that's what we're going to look at this point. Um, Also, we know something about the solar wind flow, the rate, the number of particles per square centimeter per second that are flowing out of the sun in the direction of the Earth. And that's about 270 million protons per square centimeter per second. And this is measured by a variety of spacecraft that we have in space. Number. It can be higher than that or it can be lower, but this is sort of an average. And then for the geocorona, we're just going to take an average number, which is about 10 hydrogen atoms per cubic centimeter at a particular reference, about 10 times the radius of the Earth from the center of the Earth. This is essentially measured by the IBEX spacecraft, more or less. So this gives us sort of a frame of reference. And now we, of course, have some geometric information we need. The radius of the Earth in kilometers, and the outer limit to the geocorona is about 20 times that, or 40% of the lunar distance. We're not actually going to use that lunar distance number because it doesn't really illuminate too many things that we're going to be talking about. So here's collision geometry. If the solar wind particles are entering from the right and basically approaching the disk of the planet, that gold area that you see on the left is sort of a shadow zone. Any of the atmosphere particles that are within that shadow zone are not going to be ejected. They'll just be basically driven deeper into the atmosphere. And then you have that region above the shadow zone. It's an annular region, and that's going to be the region of interaction. That's where particles can get ejected by solar wind collision. So the question is, how many of these collisions per second are we going to expect? Well, it's going to depend on the density of the geocorona. It's going to depend on the flow of solar wind particles. And we can actually work out how that works. It's going to be the difference. The active region is going to be the difference in the areas between that gold region and the outer circle. And so one can work through that you would get for that kind of a flow of particles, the number of collisions is the solar wind flow times the annular area in that diagram, out to a radius of r. And you work out the numbers and you get about 1.4 by 10 to the 29 collisions per second. So that's an awful lot of collisions per second, and that's integrated over the entire atmosphere of the Earth within that annular region that you see there. It's a projected annular region. So sounds like quite a lot. When you actually convert that into the amount of mass that's involved, you've got the number of collisions per second, and each collision ejects one hydrogen atom that has a mass of 1.7 by 10 to the minus 29 kilograms. So if you do the product of those two, you get about 240 kilograms per second of hydrogen that's being ejected by the atmosphere. If you look at that in terms of the mass loss per year, multiply that number by the number of seconds in a year, and you get 7.6 million tons of hydrogen per year is ejected from the Earth's outer atmosphere. Now, that's really quite amazing. It's also troubling because we just said that the measured number is 95,000 tons per year. So our toy model is off by about a factor of 80. Well, that's a very sad result. We're hoping to get something better than that. But the good news is that it could just as easily have been off by a million or a billion, but it's only off by about a factor of 80. So that means we have some kind of a chance that we can whittle this down into something that's a bit more precise. So that means we have to go and look at our assumptions again and see if there are any that are really egregious that we could fine tune. So where did we go wrong? Well, solar wind is mostly protons. That's an observational fact. The geocorona is mostly made out of hydrogen atoms, which is another observational fact. So there's not a whole lot of wiggle room in those two. But the thing that's the most troubling is our assumption that every solar proton collision in the solar wind removes exactly one hydrogen atom. Now, that is a number that we sort of pulled directly out of a hat. We had no justification for it, no observational justification for it. But that's the beauty of a toy model. We can start with a simple assumption, and then we can fine tune that assumption until we get something that makes sense. We might have to dig pretty deeply into the physics in order to improve that third assumption, but that's part of the fun of building an accurate model of what you're observing. The long-term thing is that we want to model the way the solar wind erodes Earth's atmosphere to get 95,000 tons per year of hydrogen. But we also want to look ahead and try to model the atmosphere of Mars and determine whether or not the solar wind was responsible for Mars losing all of its atmosphere over the 4 billion years that it's been around. I mean, that's our real target. You know, the fact that we can model Earth's solar wind abrasion rate, you know, is interesting and it's very important. But, you know, we really are looking ahead at other planets in the solar system and trying to understand why their atmospheres look the way they do and if the solar wind had anything to do with that. So, what does a collision actually look like? Well, we have to really dig pretty deep into that. First of all, let's take a look at what the geocorona gas density looks like. Here's a kind of a magnified view of those hydrogen atoms in the geocorona. You can work out sort of what the average spacing between these happens to be by looking at the density in the way that I did. If you take 10 particles per cubic centimeter and take the cube root of that and divide it into one, what you get is an actual distance, an average distance between the hydrogen atoms in the atmosphere. And that works out to be about a half a centimeter. So when a proton from the solar wind collides with one of these hydrogen atoms, it travels about a half a centimeter before it hits one of its other companion hydrogen atoms living nearby. And what happens after that? Well, that's not part of the assumption that we started with, because we said that once that collision happens, that hydrogen atom travels directly out of the atmosphere, going tens of thousands of kilometers off into space. Here, this particular physical model says the thing is only going to travel about a half a centimeter before it knocks into another hydrogen atom, and then those two are going to knock into others. And so you have this really complicated avalanche going on for every single solar proton that enters the picture. So that's what makes modeling the collision process so complicated. Let's take a look at another way of looking at this. Here is a solar proton, one solar proton in the wind entering from the right. Assume that the solar proton has an area associated with it. That area is going to sweep out a cylinder in space that is, as you see here. And depending on whether or not that cylinder encompasses one of these hydrogen atoms or not, a collision will take place. If the density of the hydrogen atoms is so low that on average there isn't one of these hydrogen atoms within this cylinder, then there will not be a collision. So by comparing the swept out area of one of these protons against the density of particles in the corona, you can get a better gauge on whether or not collisions are actually going to happen or not and how frequently they ought to happen. So if you do that math, take the diameter of a hydrogen atom, to be, I guess here we have 4 angstroms as the diameter, the radius is 2 angstroms, and you work out the math for a cylinder that has a length of that many cylinders, that many centimeters, what you get is that for that low density of the geocorona, you might only expect to get 8 by 10 to the minus 5 collisions per proton. So that's like 1 over 800 thousandths. It's not one collision, it's 1 over 800 thousandth of a collision per proton. That means you have to have 800,000 protons entering this atmosphere in order to get one hydrogen atom collision. That's another way of looking at that. Well, that's a lot less than one when we started out with. We said that every collision is going to produce one, hydrogen atom ejection. Well, this is a lot less than that, just based on the volumes that swept out by the incoming proton against the density of particles in the corona. So every solar wind particle will remove 8 by 10 to the minus 5 geocorona protons. All right, so now we have to wind that back into the calculation. And when we do that, now instead of getting 7.5 million tons of hydrogen ejected per year, we get 590 tons. Well, we're aiming for 95,000 per year. So now we are a factor of 160 times too small. Before we were about a factor of 60 times too big. Now we are absolutely gone in the other direction. So this looks like we're really modeling this whole process very well. We've now gotten one assumption that was really bad, but then we tried to make it better by putting in a little bit more physics, and we got a second prediction that was almost as bad going in the opposite direction, making the collisions too rare to really do much. Well, so what we now have to do is we have to go back to where we started. All right. Here's sort of this toy model of what the density of particles looks like in the geocorona, because we always have to go back to that. So now the question is, when you actually have a physical collision between a solar wind proton and one of the hydrogen atoms in the geocorona, what does the energy transfer look like? I mean, before what we talked about was purely geometric. There was no real physics in this whatsoever in all of the previous toy models. It was just basically geometry. All right. Now we're going to try to put a little bit of physics into this. What we're going to do is those geocorona hydrogen atoms are buzzing around in space. They're a gas, and they have a temperature of about 2,000 Kelvin units. The kinetic energy of each one of these hydrogen atoms, you can calculate that using the Boltzmann formula. It's 3/2 kT, where K is the Boltzmann constant. And it turns out that the typical average energy per hydrogen atom in the geocorona is about 4 by 10 to the minus 13 ergs per hydrogen atom. All right, that's a good number. Now let's look at the solar wind proton coming in at a speed of 400 kilometers per second. They also have a mass that's equal to a hydrogen atom, give or take. Kinetic energy of a solar wind proton is 1/2 mv squared. And if we put in the mass of a proton and the velocity in centimeters per second, we find out that the typical solar proton in the solar wind has an energy of about 1.3 by 10 to the minus 9 ergs per proton. Now, if we take the ratio of the energy in the solar wind proton and divide that by the typical average kinetic energy of the hydrogen atoms, we find out that the solar wind protons carry 3,095 times more kinetic energy than the hydrogen excuse me, than the hydrogen atoms do in the geocorona. Well, what that means is that each proton, when it collides with one of the atoms in the geocorona, it can transfer enough energy that you could have multiple collisions of that hydrogen atom with other hydrogen atoms transferring additional energy. So it actually causes a lot more particles to be ejected because they reach escape velocity from the geocorona, which is much, much less than 400 kilometers per second. It's only about 1 kilometer per second. So what we now have is sort of an efficiency factor Q, which is related to the ratio of the kinetic energies. And that Q value can be anywhere from 1 up to 3,000, depending on the kind of kinetic energy that's transferred. And so as a result, uh, the mass loss per year is 590 tons times Q. We just did the previous calculation over again, but now we multiply it by a factor of Q. So the question is, what value of Q do we need to actually eject the coronal hydrogen at the rates that we see, which is 95,000 tons per year? Well, if you choose a Q of 160, then we can match the ejection rate that we observe for the Earth against what we might predict with this very simple collision model. All right. Now the problem is, this is a bit of a cheat because we kind of knew the answer before, we did the calculation. We knew that the answer was 95,000 tons per year. And so, like setting up a pool shot on a pool table with the cue ball, we tried to create a toy model that gave us basically that number with some interesting elementary physics thrown in to make sure that we were doing the calculation honestly. Well, all right, so that's not the ideal way of doing things. But along the way, we learned a couple of important things, that there is a geometry to the collision and that there's also a collision efficiency that we have to worry about. How many hydrogen atoms are ejected for every proton that's involved in a collision? It can be one, and that gives us a definitely wrong answer, or it could be up to 3,000 if the proton inspires multiple collisions of other hydrogen atoms within the atmosphere in a kind of a branching binary way that eventually leads to the ejection, of a lot of these hydrogen atoms sort of in that last collision. So this is what the model building process looks like. You basically define a problem. You make some assumptions to simplify the equations, and we did a lot of that. You design an observational test to test the model, system to test the model. Well, we started with some numbers that we knew beforehand, like the 95,000 tons per year of hydrogen being ejected. We evaluated the model and decided the model wasn't really doing very well. And so we basically improved the model by going back to square one, but now with a little bit of additional knowledge because our previous model failed in a particular way. And so to patch that failure up, we challenged one or more of the assumptions that we started with and refined those assumptions to make them much more physics-based instead of just geometric-based. And you do this a few times, and as you do that and add more physics to the model, you start getting things which are really quite computationally unwieldy to work with. And in fact, the more advanced models, you kind of require computers or supercomputers to do, calculations at lots of time steps, and then you create three-dimensional maps of what things look like. You can sometimes put those into a movie loop, like the animation that I showed you at the beginning of the talk. And then you compare the movie loop, which is a simulated physics-based calculation, against what is actually observed. And that's sort of what the process looks like. And that's really what we did in sort of a very simplified way. But of course, we wound up with the wrong answer. Not only the wrong answer, but a massively wrong answer. But good news is, instead of being too big by a factor of 80 or too small by a factor of 160, we could just as easily have been off by a million, if we didn't know any of the physics at all and just made a, pot shot guess. So that's kind of good news that, if we do the calculations carefully, create toy models, iterate against observations, add the appropriate types of physics to the models, then ultimately we can come up with predictions that look extremely good and compare very nicely with what we see. And this is sort of a snapshot of sort of things that you could do to improve models. Our assumption that the solar wind is mostly protons. Yep, this is measured, and it's probably not a problem for any calculation that we want to do. Atmosphere is mostly hydrogen of a uniform density. Well, we know it's not a uniform density. It's denser towards the Earth and a lot more rarefied the farther out you get. We didn't put that into the model at all. We just used an average density, which obviously doesn't apply for the entire geocorona. Um, Atmosphere contains oxygen and nitrogen ions. So in our proper model, we have to treat each of these species individually as they collide with the incoming solar wind. They have different masses, so they're going to behave differently as energy is transferred. As I said, density follows exponentially with distance. That's something that we know from the observations. And for this, to put this into the model, we have to use calculus. Uh, Density varies with solar wind and X-ray heating. The hotter the corona is during times when we have sunspot maximum, the more extended and the more rarefied the geocorona gets. So that makes it more susceptible to being ejected. Well, to model that, we have to use even more calculus. Every solar proton collision removes one hydrogen atom. This collision process is very complicated to model. In fact, you can't do it by throwing equations at it. You actually have to use what's called stochastic modeling. You actually have to create models where you're looking at individual hydrogen atoms and how they scatter off each other within a gas, and then you have to follow the entire ensemble and see what it does. More than one ion can be ejected, from the geocorona at a time, depending on the energy transfer, and a variety of other things. So you basically have to have a theory or fundamental understanding of physics at each one of these steps in order to incorporate it properly in a more accurate model. And that's what makes this computationally more complicated, because you have a variety of equations that you have to essentially evaluate at each distance and at each time. But the bottom line is that you ultimately wind up with mathematical and physical models that are pretty gosh darn good. The MAVEN spacecraft in orbit around Mars measures the effect of the solar wind on the Martian atmosphere, and using a variety of sophisticated models for how this solar wind ejection process happens, plus these other three mechanisms that I showed you at the beginning, which each have their own physics and mathematics, you can actually create a fairly good model of the Martian atmosphere as it's being affected by solar wind and photodissociation and things like that. And those models can then be interrogated. Predictions can be made for what kind of a density you should expect at what particular time along the satellite's orbit. And that, once again, makes this an iterative process. There are things that you have to incorporate even in the solar wind, such that as the solar wind is not constant in time, it varies. It varies with the sunspot cycle. It varies whether there are coronal mass ejections involved or not. So, as you can see, it can be a very complicated thing to have to model. And that's the challenge of doing heliophysics. This is now, looking down the barrel of heliophysics model. And that's why it's so important to be able to do this. And as you do it, you learn more about new physical mechanisms that you might have overlooked, that you thought were not important, but then turn out to be actually important under some conditions that are relevant, maybe not for Earth, but might be relevant for Mars. And the conditions that you're proposing for Mars to define your equations there might not be appropriate if you're trying to model the atmosphere of Jupiter or the atmosphere of Venus or the atmosphere of Mercury. Well, anyway, that's sort of the end of it. And next time, I'm going to give you a little bit of a talk about the wandering magnetic North Pole and where is it now and what is it doing and why should we care? So that's it. If you have any questions, we have time for questions. So that's, yeah. Hi, Matthew.
Let's say this one is Mercury, which has no atmosphere, and
Uh-huh.
this is Venus, who has a hot atmosphere with carbon dioxide.
Right,
And this is Earth that has an ozone layer,
right.
and then it will be safe for us without getting ourselves hurt if you live in space like the astronauts.
Uh-huh.
And then this is Mars, which has partial atmosphere to it because of the solar wind from the sun.
Uh-huh.
And if it does affect the rovers on Mars, will it be safe for both Curiosity and Perseverance to take more samples for it?
Yeah, actually, it turns out that the surface rovers are deep enough in even the thin Martian atmosphere that they don't have to worry about solar wind particles. Uh, it- However, if you are a rover on the surface of the moon or on the surface of Mercury, neither of those bodies currently have much of an atmosphere. They do have a very dilute atmosphere, but it's not enough to resist solar wind particles entering and arriving at the surface. So you actually have to worry about the solar wind particles striking your rovers on those worlds. But in fact, that's really cool because that means, like the Apollo astronauts did when they put out their solar wind catchers, which were those long, tall, skinny aluminum foil things they had on the poles, uh, you can directly detect the solar wind on the surfaces of the moon, measure it, identify its element abundance and something about their speed, and things like that. So you can't do that from inside the Earth's magnetic field, but you can on the surface of the moon. So that's why the moon was used as our first direct probe of what the solar wind actually looked like in the late 1960s and early 1970s.
That makes sense.
Oh, Venus retains its atmosphere mainly because there's there's so much of it. It doesn't have a magnetic field, and so the solar wind actually penetrates into the upper atmosphere and turns the atmosphere into kind of like this comet-like thing. It actually has Venus has a dilute tail of its own atmosphere leaking out uh, behind the planet in the opposite direction from the sun. But that mass loss rate, amazingly enough, because of the density of the atmosphere and the particular circumstances, is not much different than it is for Earth. I mean, it's pretty neat. For Mars, Mars is toast. It doesn't have enough of a gravity to hold on much of an atmosphere, and what it was able to hold on to might have originally looked like the Earth's atmosphere, 4 billion years ago, but the steady solar wind erosion of the atmosphere over 4 billion years did its dirty work and essentially ejected most of it. Of course, there are other mechanisms like photodissociation and things like that, which also bore some effect. But the solar wind is the most abrasive thing. And if you're looking for habitable worlds orbiting other stars, uh, the solar winds from these other stars are really quite substantial. As it turns out, that most of the Earth-sized planets that we're finding within habitable zones happen to be around red dwarf stars, which means that their orbits are really close into where the star is. And most of these red dwarf stars are extremely active. They produce flares, they have very strong solar winds. So that's why the concern is that we're finding all of these Earth-sized planets around red dwarf stars, but probably every single one of those will have lost its atmosphere completely over the last billions of years, and there won't be any atmosphere on them, even though they're in the habitable zone. So it's that's why these space weather phenomena and solar wind issues are really important in finding you know other biospheres around other stars.
I wanted to ask, thank you for the great talk. Can we assume that Earth's atmosphere is being replenished to some extent by things like photosynthesis? But on Mars, presumably there's not anything significant replenishing the
Mhm.
atmosphere. And so people talk about terraforming Mars, but if you actually did that, is there any possibility of terraforming at a rate that would be higher than the rate of loss from the
Yeah,
solar?
no, it's no, you can't beat the solar wind. It's very hard to beat the solar wind. You have to start out with something really huge at the beginning, and then you have a fighting chance. But if you're trying to pump new atmosphere into Mars, you have to pump it in at a rate that's 100 or 1,000 times greater than what the solar wind ablation rate is. And it's just a matter of technology, as some people say. So the dreamers can say, oh, no problem. We'll just put 10 times the number of atmosphere processors on Mars. Oh, really? And who's going to pay for that? You know, uh, I mean, Venus, seems to have an unending supply of carbon dioxide from all the volcanism that's going on the surface. So it has a constant source, as does the Earth. The Earth has a constant source of atmosphere. Part of it is from the photodissociation of water vapor as it gets high up into the atmosphere. It gets photodissociated into oxygen atoms and hydrogen atoms. And where do you think those hydrogen atoms go? They go into the geocorona because they're light. So it's interesting that the loss of water on the surface of the Earth is basically what's providing the source for the geocorona in space, and that's a kind of a bad thing. But that's what we're left with.
Thank you.
Oh, there was a question about the TRAPPIST planets. Uh, yeah, I mean it's it's complicated, but it looks like there would be a problem. There are confirmed, four confirmed TRAPPIST planets. Uh, the outer one is on the outer edge of the habitable zone of the star, which means it's kind of a cold planet. But it could be warm if there's a lot of internal volcanism that would keep it warm. However, there's one on the inner edge of the uh, habitable zone, which is closer in than the planet Mercury is to our sun. And so likely that is not going to be one that has much of an atmosphere either. And then there are two others that are even closer. So that's the problem. That we don't know absolutely for sure, whether some of these habitable zone worlds actually have atmospheres or not. We know precisely where they're located and whether they are in the habitable zone of the star. But even knowing that their masses are typical of the mass of the Earth doesn't guarantee that they're going to have atmospheres because they're orbiting these red dwarf stars, which are extremely active. They produce very strong solar winds and flares, and even super flares, which are also pretty damaging to atmospheres. So yeah, but it just goes to show you that you have these tabulations of 5,000 exoplanets around 4,000 other stars, give or take. But the calculation of which ones are Earth-like has to be much more than just size and mass and location. It also has to factor in, whether they have atmospheres or whether they lost their atmospheres because of essentially space weather phenomena that are endemic to that particular star that they orbit. So that's sort of the next level of studies of these exoplanets. Um, that's what's going on now, in addition to trying to do direct detection of their atmospheres using the Webb Space Telescope and other systems like that.
And I've just had another question about magnetic fields and how Earth has a great magnetic field, and that, from what I understand, helps to protect us from the solar wind and helps to retain the atmosphere, whereas Mars has practically no magnetic field, so it doesn't have much
That's right.
protection from the solar wind. So in this context, is the overall function of the magnetic fields more protection from the solar wind rather than helping
Yes.
to retain the atmosphere in other ways?
Yeah, absolutely. If a planet has a magnetic field, then at least has a fighting chance because it can deflect the solar wind particles and even some of the solar flare particles. The problem is that these exoplanets that we're finding in such abundance in these habitable zones, many of them are going to be synchronously locked to their star. That is to say, they're always going to be showing the same face to their star as they orbit the star because they're so close in that you have basically what's called tidal torquing or tidal synchrony that goes on. Now, that's a problem because the typical orbital periods of these exoplanets seems to be on the order of uh, 10 to 100 days. And that means that the planet is only rotating like once every 10 to 100 days. In order to have a really robust magnetic field, the planet has to be rotating a lot faster than that if it has a molten core, because that's where the magnetic field is generated by the dynamo mechanism. So the troubling possibility is that we're going to find we're going to find you know worlds that look Earth-like and are in habitable zones and all of that, but because they're synchronously locked, they don't have magnetic fields, and that's just another way of saying that the solar wind basically has probably abraded most of their atmospheres. So, it's kind of interesting. There are so many factors that come into play when you're trying to determine whether a planet is likely to have a biosphere of some kind or not. Uh, and this is an important factor. Of course, Europa does not have an atmosphere, but it may very well have a biosphere that's subsurface underneath the ice. And it's getting plenty of energy from the tidal stresses that Jupiter applies to keep the interior warm. So, there might be situations like that that occur amongst these exoplanets. We just don't know at this point. Atmospheres may not necessarily be absolutely necessary, but we tend to be biased with what we know and the kinds of life that we know about, which is us. Okay, well, we aren't any more questions. I guess we can go off and have dinner and cogitate on how bad things can happen to good planets.
And see you on April 1st.
On April
No, April 22nd.
April 22nd, yes. I don't do